we're going to take a look at real number sets. So we're going to first define what this is. So real numbers are simply all numbers that can be located on a number line. All right, so we see these, all the time. We typically draw a little line, zeros in the middle, and we go out and we have sort of the normal numbers that we write on there, 1, 2, 3, -1, -2, -3, and then we have numbers in between. So for example, between 0 and 1, we might have 0.5. Okay. So those are our real numbers. We also have something called imaginary numbers. So these are numbers that are not real, so we wouldn't represent them on our standard number line there. So an example of what these look like are a number such as 3i or -6i. And we're not really going to be dealing with these a lot. We're just going to know that they exist and move on from there. So we also need to know what a set is. And a set is simply a group of things, right? And in this case, we're looking at a group of numbers, right? So we can take the numbers, say 2, 3, 4, 5, and 6. We can write them as a set. And the way we do this is using these little exaggerated, didn't draw that very well, brackets here. All right, so they're different from parentheses. They're these kind of squiggly brackets, and they're what we use to denote a set or a group of numbers or objects, or really anything else. Okay, so numbers can be broken down into specific categories that will give you an idea of what characteristics the number has. And I actually like to work with this list backwards. So we're going to start from the bottom and work our way up. So we're going to start with the natural numbers. These are the numbers that we are most familiar with. We often call them our counting numbers. All right, they're the numbers that we would learn first as a small child, learning how to count objects. So they're numbers such as 1, 2, 3, 4, all the way up to infinity. So if we're thinking about a number line, we have 1, 2, 3, 4. So no decimals, no fractions. This set starts at 1 and continues counting upwards. No decimals, no fractions, no negatives, no 0. All right. So as we work our way up this list, we start adding more and more characteristics that numbers can have. So here, natural numbers were very restricted, 1, 2, 3, 4, 5, 6, 7, so on and so forth. We're going to go to the whole numbers, okay? So the whole numbers are a group of numbers where we're going to keep all of our natural numbers, but we're going to tack in 0. So this is a group of numbers described by the set 0, 1, 2, 3, 4, and all the way up, continuing the pattern to infinity. So the only difference between natural and whole is that whole numbers have 0 in them. All right, so we're starting to fill in that number line. Okay, next up, integers. So we're going to be adding some numbers here to our kind of building group of numbers. And what we're going to add in with the integers is we're going to start taking a look at the opposites of our whole numbers, or the opposites of our integers. So it's the set of all of our whole numbers and their opposites. So what that means is, what's the opposite of 1? -1. The opposite of 2? -2. So we're going to be adding those in. So now not only do we have 0, 1, 2, 3, and going up, we also have -1, -2, -3, and counting down. Okay, so still no fractions, still no decimals, no square roots, nothing like that in the natural, whole, or integers. Okay, adding even more possibilities. So we're going to go up here and take a look at what we call a rational number. all right? So up to this point, we haven't had any decimals, any fractions, nothing like that. But we know on our number line, in between 0 and 1, there are all sorts of numbers in there. 0.1, 0.2, 0.3, 0.44444. They all exist in there. And we need to give those numbers a category to belong to. And this is where they belong, in the rational numbers. So this is any number, any real number that can be written as a fraction. Oops. Fraction of integers. So that basically means if we can take our little fraction bar and I can put any integer that I want in the numerator and any integer that I want in the denominator, and that creates a rational number. Okay, so any number that can be described like this is a rational number. So let's look at some other ones. Let's look at, say, 2/5, right? So 2 is an integer. If you look down at our integers, 5 is an integer. Well, if we put 2/5 in our calculator, what would that look like? Well, 2/5 is really 0.4. Okay, so we can have fractions and we can have the decimal version of that fraction also in the rational numbers. Let's look at another one. Let's look at, say, -2/3. Okay, -2 is an integer. 3 is an integer, so we got a fraction of integers. If we put that in our calculator and we get that out, we get -0.66 repeating. Okay, so another decimal. So if we're looking at this, we can say that a number is a rational number if it is a fraction of integers, or if it is a terminating or repeating decimal. So 0.4 would be our terminating decimal. It ends, it's 0.4, there's nothing after it. -0.66 going on 6666 forever, that's our repeating. So we know what it's going to repeat every single time to infinity and beyond. So those are all the numbers that belong in our rational numbers. So what are these irrational numbers? So all we've done is we put IR in front of that word rational. So what does that do? Well, that just means not. All right. So the irrational numbers are everything that does not belong in the rational number. So everything that's not rational. Okay. Because we have 0.4 and we have that -0.66 repeating, but we have other numbers that exist that don't terminate, other decimals that exist that don't terminate and they don't repeat. So one of the most famous numbers is pi, right? And that's approximately 3.14159, and it goes on forever and ever and ever, but it doesn't have a predictable pattern. Okay, so that is an irrational number. It doesn't terminate, it doesn't repeat for that decimal, and we're going to go ahead and classify that as irrational. So what's another good example of an irrational number? So a square root often will be categorized in irrational numbers. Not all of them, but many of them. So let's say the square root of 2, for example. This is approximately 1.414213, and it goes on forever and ever and ever with no predictable pattern. So we would classify that as irrational. Okay. Now, I want to go back to the rational numbers for just a moment and point out some guys that live in the rationals but might trick us and might look like an irrational number. So for example, we take a square root, which we think, oh, maybe that's irrational. But really, what if it's the square root of 9? Okay, so if you're really good with your perfect squares, or if not, head to your calculator, we know 9 is really just 3 squared. Squaring and square rooting are inverse operations, so we would know that the square root of 9 is really just 3. Well, Rational numbers need to be expressed as a fraction. Can I express 3 as a fraction? Absolutely. 3 over 1. So the square root of 9 is really a rational number. Okay. A great way to represent these numbers and for us to help remember where everything belongs is to take a look at a Venn diagram. Okay. So using a Venn diagram, we can classify these numbers in a super simple way. And even though each of these sets of numbers has infinitely many numbers in it, we can kind of fudge it a little bit and think about the bigger sets and the smaller sets. Or as I like to say, the most restrictive and the least restrictive. So I'm going to start from the inside out, just like we work from the bottom up. So our most restrictive set, or you can think of it as our smallest set of numbers, are these natural numbers. So that's our 1, 2, 3, 4, so on, okay? And then we move out. We get into a bigger circle. So we're getting least restrictive, right? We're letting more numbers in. And that's when we get to our whole numbers. So this we've added in 0. 1, 2, 3, and so on. So 1, 2, 3, 4 are all still natural numbers, but they're also whole numbers. And then whole numbers are just saying, hey, we're letting 0 into the party now. Okay. Now we're going to get even less restrictive. We're getting a bigger, we think of it as a bigger group of numbers. Okay. So now we're adding in, we're letting in the negatives, but we're still keeping in the whole numbers, which keeps in the natural numbers. So you got to remember that if something's in the integer circle, well, the integer circle has the whole number circle and the natural number circle in it. So a number can be an integer and a whole number and a natural number all at once, but not all of them. All right, so then we get even less restrictive and we get into the rationals. All right, so now we're letting in the fractions, we're letting in the decimals. We have our 1/3 or 0.22, 0.33 repeating, 2/5, -7/4. All of those guys are now allowed in the rationals. But remember, every integer can be expressed as a fraction. 4 over 1, right? So that is a rational number. It can be expressed as a fraction, but it's still an integer. And if we look at the wholes, oh, it'd still be a whole number, and it'd still be a natural number as well. Okay. And then we get to this other circle. So we look at the right and we see this as a completely separate circle. And we remember that that IR there means not rational. So if we look at that rational circle, we want to think, okay, what are the numbers that don't belong inside that big rational circle? And here's where we get our numbers with pi. So pi or -3 pi. And we also get some of our square roots, square root of 2, or the square root of 5, or -3 times the square root of 7. All of those belong in our irrationals. Okay, and then we branch out into this even bigger box of the real numbers, which is what all of these numbers belong to. The rationals, the integers, the wholes, the naturals, and the irrationals are all still part of that big umbrella of real numbers. So how are we going to use this? Why do we want to know this? What are we going to do with this information? Our goal is to be able to look at a number or a group of numbers and precisely name what group they belong to. And we always want to say the most restrictive name, right? The smallest circle that we could be in, because that's going to give whoever we're talking to the most amount of information. So refer back to that Venn diagram that we were taking a look at before. And when I do this, I like to start from the inside and go out. And I'm going to ask myself the question, do these numbers belong in that group? And when I hit my first yes is when I know the smallest group of numbers that this entire set belongs to. So the first one we're going to start with is the set of numbers 2, -5, 9, -25, 0, 31. So I'm going to start from the inside. I'm going to start with the natural numbers. So are all of these numbers natural? 1, 2, 3, 4, 5, so on. No. 0 is not a natural number. Natural numbers don't have any negatives. So the smallest group isn't the natural numbers. So we're going to go slightly bigger. We're going to look at the whole numbers. 0, 1, 2, 3, 4. Okay, so now 0 is fine, but -25 and -5 aren't part of the whole numbers. Okay, so let's go one bigger. Integers. Are all of these numbers integers? Well, we said the integers were the whole numbers, their opposites, and the only thing we couldn't have were decimals, fractions, things like that. So I look at this and I say, well, there's no decimals, there's no fractions. 0 is okay, 31, -25, 9, -5, 2. Yep, those are all integers. So I would describe this group, all of these numbers, as belonging to the integers. Okay, let's take a look at the next one. 2.3, -6, 2/7, -3, and 4/5. Starting from the inside out. Are these all natural numbers? No, none of these are natural numbers, right? So natural numbers, we don't have any negatives, we don't have any fractions, we don't have any decimals, and we don't have 0. Well, these are all either negative, a fraction, or decimal, so they definitely don't belong. All right, moving out. Are they whole numbers? Nope, none of these are whole numbers. All whole numbers does is add in 0, and we don't have 0. Are these integers? Well, let's take a look. Integers don't have decimals, don't have fractions, but they can have the opposites of the whole numbers. So -6, we're good. -6 is an integer. But we still haven't fit all of our numbers in, so we keep having to go bigger. Rational numbers. So rational numbers are where we introduce terminating decimals, repeating decimals, and fractions. 2.3 is terminating. 2/7 is a fraction of integers. -3 and 4/5 is a fraction of integers. So now we've found something where all of these numbers belong, and that's in the rational numbers. Okay, last group. So if we're looking at this guy, one thing we might want to notice is that we have the number pi. So when I look at that, I want to immediately think, we're not going to be rational. And if we're not rational, it can't be an integer, it can't be a whole number, and it can't be a natural number. So you think about those circles, those are inside of the big rational ones. So if we're not in the big one, we can't be in any of the little ones. So we want to look to the right in the Venn diagram and over at the irrational numbers, okay? And I want to confirm that every single one of these is an irrational number. And looking at them, they are. 3 pi is irrational, 5 times the square root of 2, negative square root of 5, 2 pi over 3. They're all irrational. And you might think this guy right here, 2 pi over 3, well, it's a fraction, but it's not a fraction of integers because 2 pi is not an integer. Okay, so we got to be very careful with that. So this would belong to the group of irrational numbers.